In this video, we're going to learn how to compute a p-value when we've done a one sample proportion hypothesis test. So first off, a p-value is basically an area under a curve. So we've done this before, talking about the normal model before. Now we're just starting at a point and then finding the area out to a tail. In other words, just a probability. You have to pay attention to what tail test you have, because the tail of the test determines which direction you're going to find your area. So if you have a right tail test, you're going to find the area to the right of a test statistic. Left tail test, find the area to the left of a test statistic. And then if there's a two tail test, you actually have two areas to find. It's pretty easy to find them though, because once you find one, you double it, and there's your p-value. We're going to talk about that in a further example. So we're going back to our example where we have 1,000 students and we're comparing those completion rates for students who had started at the beginning of the Great Recession. So the first example, we were taking our percentage of 52.9% and trying to see if we could say that more than half the students have completed college within the 6 years of starting. So just recall our null hypothesis, the proportion equals 0.5. The alternative, what we're trying to show, is greater than 0.5. And in the previous video, we had found that the test statistic for that sample was 1.83. So here's a picture of what we're trying to do. Here's our test statistic. We found that. Boom. And we're trying to then find the area in the tail. I know that I have a right tail test. I have that word more, so that's a right tail test. And I want to find the area, how much area is above 1.83. Now I could use our statistics book and go to the Z table, look up 1.83, make sure to find the area in the right tail, but I'm going to use StatCrunch instead. So I'll show you how I got here. I'm going to go to Stat, Calculators, Normal, because I have a normal model. And it's standard normal, so the mean is 0, the standard deviation is 1, and I want to find the area that is above, because of our tail test, 1.83, and then I push compute. So this area that's shaded right here, this red area, is the p-value. And down here the probability is 0.0336. So the p-value for my hypothesis test is 0.0336. So I can type it in here, 0.0, or write it in here, 0.0336. Now, I did a little bit of rounding there, so when I compute this hypothesis test with StatCrunch in a later video, I might get a little bit different answer because I had to do some rounding at some point. This test statistic might be a smidgen off, so that would then throw off my p-value just a little bit. All right, down to the second problem. We wanted to see if there was a change, if the sample proportion had changed from a prior year's estimate of 56.1%. So that word change, that's our clue that we're going to do a two-tailed test. So recall these are our hypotheses. The null hypothesis, the proportion is equal to 0.561. The alternative is that it's different. And the test statistic from our data was negative 2.04. So our sample proportion, 52.9%, was just over 2 standard deviations below the mean. So I need to find this area in the left tail, and then if I double it, I'll be finding this symmetric area in the right tail. Add those together, and that's our p-value. So I'll go ahead and start here. Mean of 0, standard deviation of 1. I want area below, and we'll type in negative 2.04 and compute. So this area in the left tail, now I could have chosen to do a right tail, but I wanted left tail since I had that negative to start with. The area below negative 2.04 is 0.0207. 0.0207. So that tail, 0.0207. So there's a reason why we end up doubling this area, and that has to do with that level of significance. Back when we computed critical values, we took the 0.05 and we divided it in half. So we had 2 small regions. Well, this is kind of going back full circle. We found the area of 1 small region. Now we need to double it and get back to a total. So we have the area in the other tail, 0.0207, and our p-value in all, p-value is equal to 2 times 0.0207. So that is going to be 0.0414. So our p-value is just over 4%. It's not 2%, it's just over 4%. If you do any sort of technology to find a p-value, read the p-value from the output and you're done. The only time you have to do this extra step of doubling areas is when you work by hand and you're finding one tail in a calculator or StatCrunch or working by hand. The computer already doubles the area. It already knows what you're doing. Then the last problem, we had the other type of test. We had that left tail test. We're trying to see if our proportion is significantly less than 56%. So our hypotheses were p equal 0.561, and then there's our left tail, p less than 0.561. We got the same test statistic, negative 2.04. So I'm actually not going to go to the calculator because I already have the answer. I used it from the last problem. I calculated the area in that left tail in the last problem. And since I had the exact same test statistic, negative 2.04, negative 2.04, the area in that left tail will be exactly the same. So for this problem, the p-value equals 0.0207. So what does all this mean? Sure, we have p-values, but the way that we would interpret a p-value, it is, I'll use the last problem as an example. There is a 2.07% chance we get a sample proportion less than, what was our sample proportion? 52.9%. I'm going to emphasize this word, given that the null hypothesis is true. All right, so all of that says, okay, we get the 2%. It's the area in the tail. It's a 2% chance, but of what? It's the 2% chance of being behind that test statistic, of being less than 52.9%. Remember, we just scaled down our normal model that was centered at 56.1%, and we scaled it to standard normal. That's what the z-score did. So the 2% chance of being below negative 2.04 is the same 2% chance that we are below 52.9 with a model that's centered at 56%. So imagine just like taking a photocopier and expanding or shrinking a document. That's what we've done here with our z-score. We've just kind of slid it around and changed the shape a little bit. Now this last part, given that the null hypothesis is true, that's the important part because we fixed the center of the model. We made an assumption that the center was at 56%, 56.1%. So if this proportion changes, if your center changes, then it's going to throw off your proportion because the curve won't be in the same place anymore. If you slide it further to one side, this area is going to change because that shape of the curve changes. So this p-value is the chances of getting something more extreme, further in the tail, than what you already have. That's a pretty small percent. just over 2%. If you take lots and lots of samples, there's about a 2% chance that you get something even worse than 52.9%.